Okay, so here was your next clicker quiz question. It asked you to predict the signs of the enthalpy and the entropy for the reaction of carbon tetrachloride liquid vaporizing to the gas state. So let's think about how the enthalpy changes. Remember that enthalpy is potential energy, and in one case, we have all the particles in close proximity to one another, and presumably they're going to be attracting one another because that's how molecules typically are. And then they're getting more spread apart into the gas phase. So since they are attracting one another and working against the force in order to expand, raises the potential energy, therefore the delta H is going to be positive. So delta H naught is going to be greater than 0. Also, you should remember that the transition from liquid to gas is increasing the entropy. There's a lot more ways to arrange the system in a gas than there is to arrange the system in a liquid. So the entropy is also going to be positive. And that's the correct answer right there. Okay, let's move on to the equilibrium of solutions. Now, a lot of detail is presented in the book, and I will let you follow most of the math from that part of the chapter. And it's going to be a fairly similar derivation to what we had when we looked at the equilibrium constants of ideal gases, though there are going to be a number of subtle differences. So if anything's confusing, feel free to ask me about it in office hours or on the discussion forums. The first key assumption that we're going to make is that the chemical potential of a certain component of the solution is going to be equal to whatever the chemical potential of that substance is in the pure state, plus, for, remember, real solutions, it's going to be RT times the log of the activity of that particular component. Okay? The next assumption that we're going to make, and we made a very similar one when looking at the equilibrium for ideal gases, we have nu I, which is the stoichiometric coefficient. So if we have a reaction of the type alpha A plus beta B is in equilibrium with gamma C and delta D, each of these are the nu symbols, alpha, beta, gamma, delta, multiplied times the chemical potential of that particular component in the pure state, plus RT times the sum over all the components, the stoichiometric coefficient, the log of that activity. And we can take this coefficient and bring it inside the log, use the rules of logland, and this whole thing can just become the log of the activity raised to the power of the stoichiometric coefficient. That is also possible. And all of this equals 0 at equilibrium. But this expression right here is the standard Gibbs free energy for the reaction. So we can say that delta GR is equal to negative RT, sum over the components, log, natural log, AI nu I, like so, and that this is sort of an effective equilibrium constant. So log K, the equilibrium constant like that. And the way we were able to do that was to use the rules of logland to convert this summation on the outside of the log to a multiplication on the inside of the log. So that means that this equilibrium constant is going to be equal to the activity of component A and the stoichiometric coefficient of A, and then the activity of B, stoichiometric coefficient of B. These are multiplied times each other, on and on and on and on like that. And so we have to multiply all of the activities times each other. Though, of course, the the products are going to be in the numerator of a fraction, and the reactants are going to be in the denominator of that fraction. When we're dealing with solutions, us chemists typically prefer to work in concentrations, not activities or mole fractions or anything like that, if possible. So now I'm going to show you how we're going to be able to express the equilibrium constant in terms of concentration and not mole fractions or activities. And some of you have asked about this before, so now is our opportunity to satisfy your curiosity. I told you on previous slides that the activity is going to be equal to the activity coefficient multiplied times the mole fraction. Let's just consider that mole fraction for a second here, briefly. That is the number of moles of I over the total number of moles, okay? And then I can take this fraction here and multiply times 1 liter over 1 liter, because that's just the same as multiplying times 1. And what do I get? I get N sub I divided by 1 liter, N total divided by 1 liter. But this right here, that's just the concentration of I. And this right here is some sort of total concentration. Now, when we're formulating equations of this type, we want to be able to use the standard state concentration, which is 1 molar. All right? So this equals Ci over the total concentration of all the species in the solution. And I'm going to include the standard concentration, standard state concentration here. So what are we going to do with this term right here, that pesky term right there? Well, we're going to rewrite the chemical potential in the solution is the chemical potential in the pure state of that substance plus RT natural log Ci C naught multiplied times C naught over that C total. But then, of course, I can just use the rules of logland and write RT log C naught over C total plus RT log Ci over C naught. And this whole term right here can just be lumped in with that chemical potential right there. And so I get a new chemical potential that I'm just going to label with a C right there to indicate that it's not the same as that chemical potential up there, but now we're going to have an RT log Ci over C naught. Now, the book's not very clear about this. The book just sort of jumps straight to this one right here without explaining where the C naught comes from. But this is the correct process for getting that expression for the chemical potential. Well, now that we have that, we can write down a equilibrium constant here. The equilibrium constant is going to be the activity coefficient of substance A raised to the stoichiometric coefficient of A, concentration of A over standard concentration, also raised, multiplied times activity coefficient of the next thing, concentration of that thing, standard concentration, coefficient, on and on and on and on. But there's a shorter way to write this. You know that if I have a symbol, Greek symbol sigma, capital sigma, this means to add terms. But if I have a capital Greek letter pi, that means multiply terms. So the shorter way of writing this is just capital pi and then activity coefficient I, stoichiometric I, concentration, standard concentration, coefficient, like that. And that's our equilibrium constant for concentrations of solutions. Now for ideal solutions, that activity coefficient just equals 1. So our K just becomes a multiplication of all the concentrations divided by the standard concentration raised to their stoichiometric coefficient. So why do we care so much about these equilibrium constants? Well, for the same reason that we do in the case of ideal gases. We can relate this expression to a Gibbs free energy of reaction. If we plug in our equilibrium constant here, then that allows us to get our Gibbs free energy of reaction. But maybe we want to go the other way too. If we know the Gibbs free energy of reaction, like from the back of the book or something, then that's going to allow us to find the equilibrium concentrations of the solution. And that's a very powerful capability.